Okay, thank you everyone. Bonjour and bienvenue. A very warm welcome. My name is Simon Hamilton and I'm going to be the host and moderator for this amazing talk today and panel discussions. Just a little bit about myself. I'm an educator and a designer. I'm an associate lecturer and the practice leader at the Royal College of Art in London. And in addition to that, I'm also design director for Yes Colours, which is a relatively new British paint brand that is sort of challenging the industry by championing neurodiversity, sustainability, and well-being through colour. So that sort of puts into context who I am. So I'll be looking after you and the speakers today, and we're going to be talking about natural intelligence. Just a little bit about the dna.paris Design Awards Conference. It unites designers, architects and thinkers like yourself, and who explore diverse forms of intelligence, natural, cultural and human, and how they can shape our collective response to environmental and social challenges. This event celebrates collaboration, curiosity and creativity at the intersection of design and nature. So the first thing we want to talk about, we have a wonderful speaker. It's a Biomimetic future, and our first speaker is Michael Pawlyn of Exploration Architecture. He's a London-based regenerative architect and leading voice in biomimicry. He opens today by exploring how natural systems can inspire a new design paradigm. Michael examines the shift from sustainability to regeneration, encouraging designers to become co-enablers of ecological balance. By learning from the structures and efficiencies found in nature, he reveals how architecture can evolve into a restorative force. So, welcome, Michael. The floor is yours, and Michael will now have a presentation. Thank you.
Great. Well, thank you for that introduction, Simon. Thank you all for coming. So the short version of what I'm going to be saying today is that we need to meaningfully address the planetary emergency. We need to rethink how we design and rethink our role as humans. And the solutions to our nature crisis are to be found in nature itself. So before I get into that, I want to say a few words about this slide. So it's often said that it was the first photograph taken of planet Earth from the moon, which started the environmental movement. And in many ways, I find this a more compelling image. So this was taken by the Cassini spacecraft. As it was passing Jupiter, it turned around and it took this amazing photograph of planet Earth, that little pale blue dot. And I think it's clear from that photograph that no one is coming to our rescue. Whatever happens is up to us. This also makes me think about our place in the cosmos and our place in deep time. And there's a scientist writer called Janine Benyus who has a very good way of conveying the length of deep time. She encourages people to imagine the whole history of planet Earth as if it were represented as a single calendar year. And imagine you're at midnight on New Year's Eve and you're looking back over that year. What you'd find is that the first life forms appeared in March. It took until late August for that to turn into multicellular life forms. On the 18th of November, things absolutely exploded into a diversity of amazing animal forms. The dinosaurs emerged in early to mid-December. They disappeared the day after Christmas. And the first hominids arrived at 8 p.m. today, the 31st of December. The whole of recorded history has flashed past in the last 30 seconds. In the last 2 seconds, humans became a geophysical force affecting our whole climate. In the last third of a second, that's the time I've been alive, we've extinguished more than 2/3 of the wild animals on planet Earth. So it'd be easy to conclude from this that we are racing towards extinction. If we carry on as we are heading in a very dangerous direction. But in that last third of a second, we've also developed phenomenal technologies. We've developed amazing scientific knowledge. We actually have nearly all the solutions that we need to address this challenge. But at the moment, it's not happening fast enough. And I also think we are placing a bit too much faith in technology. There are a lot of very powerful people who would like us to believe that we don't really need to make major changes because technology is going to save us. And I don't think that's the case. I think more importantly, we actually need cultural shifts. And that's part of what I'm going to be talking about. So I'm going to be making the case for a kind of deeper philosophy of biomimicry. I guess the most common examples of biomimicry would be examples like train nose cones or the upturned wingtips on planes. And those are all valid and real, but I actually think there's a much more transformative case that is possible. We can use biomimicry to actually rethink how we design from first principles. And one of the biggest influences on me and my thinking, I've recently rewritten my book, and one of the biggest influences is a philosopher called Freya Matthews. And she has set out a kind of deeper philosophy of biomimicry. And she talks about a book that you may have heard of. It's called Cradle to Cradle by Michael Braungart and Bill McDonough. And in that book, there's a point where the authors say, just imagine you are the manufacturer of a hair gel. And what you should do is you should think about the river that hair gel will end up in. And you should ask yourself, what does the river want from the hair gel? So Freya Matthews says that that's along the right lines, but it doesn't go far enough. What we should be asking is, what does nature want us to desire in the first place? So that we can actually be part of its creative unfolding, and we can get to the point where we are co-evolving and participating as nature. That's the challenge that's coming into focus now. I think after 30 years of sustainability, it's really quite obvious now that just trying to be a bit less bad in everything we do was never going to be enough. We need to get into the realms of actually having a net positive impact. The next thing that I think is going to become very obvious is that everything we do needs to be aligned with life. We need to learn to integrate everything we do as humans into the web of life that supports us. All right, so that's a massive challenge. How do we go about this? Well, I think it all starts with systems, understanding living systems so that we know how to integrate into them. Ecosystems have some very important characteristics. They're very interconnected and interdependent. They are zero waste, they run entirely on solar energy, and they're regenerative to their places. They actually enhance life. Most human systems have done the opposite. They tend to be fossil fuel based, they're extractive, they're quite wasteful. And there are a number of projects that have mimicked the characteristics of ecosystems. So this is an early example. It's called Kalundborg in Denmark. And here, a number of industries and land uses all connected up so that the waste from one part of that system became the input for something else in that system. So it's like these are all equivalents to species in an ecosystem. And that achieved really quite remarkable things. It achieved 240,000 tons of CO2 saving per year, $10 million of waste savings. But there are some more recent projects that I think demonstrate the characteristics of ecosystems more cogently. And one of my favorites is one called the Cardboard to Caviar project. And it's quite a coincidence that we're in an old cardboard factory. So this project started involving people with disabilities collecting cardboard from shops and restaurants. And then that cardboard was shredded and sold for horse bedding. When that was soiled, they were paid to collect the manure and the cardboard, and they put it into wormery composting systems, which produced worms, which they fed to Siberian sturgeon, which produced caviar, which they sold back to the restaurants. So it's created this kind of alchemical loop, turning a low-value material into a high-value material. And then the guy that set this up just kept on adding more and more elements to this system. He was given an area of land next to a water treatment facility, and this was former industrial land. It was quite degraded, but using treated fertilizer sludge from the water treatment facility, he and his team were able to plant willow biomass, which ran a biomass boiler to keep the fish growing in winter. And then he started involving kids on drug rehab programs, growing vegetables to produce further fish food. They restored more industrial land, and they planted apple trees and other orchards. So that was another thing to sell to the shops and restaurants. They then found that there was a bakery nearby producing lots of moldy bread. And apparently you can grow maggots on moldy bread with none of the smells of meat-based production. So that was another thing for the fish. Then they redesigned the treatment system for the fish tank water, and they used a salad crop, watercress, to take the excess nutrients out of the water. So that was another thing to sell to the shops and restaurants. And then they worked with ex-service personnel with post-traumatic stress disorder on building a fish smokehouse to add value to the fish. And this system kept on growing. And just like real ecosystems enhance in diversity and resilience over time, there was a real sense in which the more this grew, the more the number of possibilities increased. And this, I think, shows a way in which we can rethink our conventional linear extractive systems and steadily move closer and closer to the way that real ecosystems work. There are some examples of how this has been applied to urban systems. This is an extension to Stockholm. It's called Hammarby Sjöstadt, where they deliberately brought together cycles of food, energy, materials, and waste. And by doing that, they were able to achieve some really remarkable synergies and move towards a highly productive system that is zero waste and runs entirely on solar energy. And that's the potential, that we could create a future that is entirely run on solar energy with zero waste, and all physical resources have been integrated into natural systems. Now, moving on to materials, which is the next step in rethinking design from first principles. We tend to make things in ways that are difficult to incorporate it into those kind of systems. So learning from the characteristics of ecosystems is a good way of helping us rethink this. We often make things in ways that use huge amounts of energy and make them difficult to recycle. The image you're looking at here, these are the spinneret glands on the back of a spider. And the closest thing that humans have made to spider silk in terms of strength is called aramid fiber. And to make that, what you have to do is you take petroleum and you put it in, you boil it in concentrated sulfuric acid, and then you pile on extremes of pressure to get the molecules into place. Out of that, you get your fiber and masses of toxic waste. So huge amounts of energy, lots of pollution, and all that to do the same as a spider does at room temperature with raw materials of dead flies and water. And that's the potential. If we learn from the way that nature makes things, we could start to make things in a much more intelligent and efficient way. So, for instance, there are two ideas in biological structures. I'll explain here. One is called hierarchy, and the other is interfaces. So hierarchy is the idea of structures within structures. If you look at the Eiffel Tower, you can see that it's got trusses within trusses within trusses. So that's 3 levels of hierarchy. Most of the structures we build have 1 or no levels of hierarchy. In biology, you can often find examples like the lobster carapace that has 7 levels of hierarchy. And each level enhances the performance and efficiency of that material. Then the idea of interfaces, well, the image on the right there, that is a highly magnified view of a seashell called an abalone. And it's made of these layers of calcium carbonate discs, and they're connected together with an interface of flexible protein. And that gives it amazing resistance to cracking. So at an ordinary chemical level, it's almost identical to ordinary blackboard chalk. But because of those interfaces, it achieves 3,000 times the toughness. And my studio designed a house based on similar ideas. So we created a curved form to create inherent stiffness. And then the roof is built up out of layers of tiles, very similar to the abalone. And in relative scale terms, it's thinner than eggshell. And we're pretty confident that would use about half the amount of material of a conventional house. I think we're going to see a big shift towards the increasing use of biomaterials for lots of reasons. They're easier to integrate into living systems, and they also absorb CO2 in their production. This is a type of insulation made by a company called Biome. So you can make this from waste plant material with mycelium. It's completely non-toxic, it's high performance, and it's fireproof. And at the end of its life, you can just put that literally back into a compost heap. There are ways in which we can design out glues. So adhesives are often quite toxic. This is a species called a sandcastle worm, and it's evolved two-part epoxy which can set underwater. This is a technology called biorock. It's a way of growing structures in the sea through electrodeposition of minerals. So if you put a thin piece of steel in the water and you pass a very low electric current through it, you get minerals building up on that, calcium carbonate and magnesium hydroxide. And it can be as strong as reinforced concrete. So in my office, we designed a building, and the idea here is that it can be completely grown in seawater. It's a performance space. It's called the Biorock Pavilion. And when it's fully grown, you lift it to the surface and you put it on a barge, and then you could moor it, I don't know, on the Seine or in the river, on the River Thames, and use it for performances. Concrete is one of the big problematic materials. Roughly 8% of the greenhouse gas emissions globally, they come from concrete production. But the nearest biological equivalent is coral. Very similar. It's a large-scale mineral structure, but whereas concrete production produces about a ton of CO2 for each ton of concrete, coral grows by taking carbon out of its environment. And we really ought to be doing the same thing, researching methods of biomineralization and geomineralization. And then the potential is that we could create buildings where all the materials are actually planet positive, that take carbon out of the atmosphere, and all of those materials can be stewarded within closed loop cycles. Moving on to structures now, there's a useful summary here that comes from someone called Julian Vincent, who said that in nature, materials are expensive and shape is cheap. And what that means is that you often find structures that are really quite complicated, and they achieve amazing efficiency by putting the materials exactly where they need to be. And there are now software tools that allow us to get closer to this, aiming for a kind of theoretically perfect biological structure, so that those elements, the alignment of those, there's nothing accidental about that. Those are orientated so that it can deliver, or it can conduct those forces down to ground with an absolute minimum of materials. And there's a Dutch designer called Joris Laarman who designed a beautiful 3D printed bridge which could be printed to cross a canal. This is a table that my studio designed for an exhibition. And again, there's nothing accidental about that. That's trying to get as close as possible to a theoretically perfect structure. And it's based on bone and tree growth patterns, and it's 3D printed from a biological polymer. So that's taking carbon out of the atmosphere and then printing it into a really, I think, beautiful and very efficient structure. And this doesn't all have to be high technology. In fact, a lot of it can be very low tech. This is a way of combining a 3D printing rig with very basic material. So it 3D prints with mud. And I would argue this is actually getting quite close to the way that animals build their shelters. So they don't use a lot of energy transporting materials over hundreds of kilometers. They just bring evolved ingenuity to the materials that exist on the site. We used biomimicry a lot on the design of the Eden project, and that helped us achieve an incredibly lightweight structure. So that enclosure, that's not glass, that's a lightweight polymer. It's called ETFE, and those are inflated pillows. And those are about 1% of the weight of double glazing. And that resulted in all sorts of kind of knock-on savings. So with such large, lightweight pillows, we needed less steel. With less steel, we were getting more sunlight into the building, so we didn't need to put as much heat in winter. And with less overall weight in the superstructure, there were big savings in the substructure. The final category I'm going to talk about today is water. And water, I mean, it's obvious to say, is kind of fundamental to all life. And by handling and managing water more intelligently in our buildings and cities, there's potential to create far more life, to allow for more biodiversity, to massively improve the quality of the air. And this is a wonderful scheme. It's called Sponge Cities, that was developed by some people in China. And they're really trying to mimic the performance of an actual ecosystem in cities. And what we really need to be doing is also looking at the kind of whole watershed and renaturalizing rivers and planting more forests in those upland areas so that you don't get such big flows of water and flooding further down the stream. Now, one of the really promising things about biomimicry is that it draws on solutions to really quite constrained challenges. So, for instance, in deserts, you can find amazing adaptations to water shortages. This is a type of lizard that can drink with its feet. If it's standing on damp ground, the water tracks all the way up its skin, up to its mouth, and then it licks its lips and looks rather pleased with itself. And there are other examples. So the prickly pear cactus, those spines, those have a very specific geometry to them, which essentially sucks water out of the air. Droplets of water form on the tips and actually track along those spines, even against gravity, up into the body of the plant. Camel's nostrils are also a miracle of water recovery adaptation. They recover nearly all the moisture in the air that is breathed out by a camel. And overall, what I think we should be doing is when we're designing a new building or a new piece of city, we should be looking at how a mature ecosystem in that part of the world functions. How much carbon does it sequester? How much water does it filter? How much oxygen does it produce? How much food does it produce? How much wildlife does it accommodate? And those should become the targets for our new piece of city. We're nowhere near that at the moment, but there are sufficient examples of projects that do bits of that for me to be convinced that that is possible. So I think we're going to see more and more buildings incorporating vegetation. We need to find a way to do that without increasing the CO2, the embodied CO2 of the building. But there are lots of advantages to this. It creates a cooler microclimate, it creates habitats, and it's good for our well-being. One of the biggest differences I think we'll see is in the spaces between buildings. So this is in the capital of South Korea, in Seoul, that used to be covered by a 6-lane elevated motorway. The mayor tore that down and restored the river and created this amazing amenity. And there are further quite amazing things we can learn from nature about how to transport water. So this shows a principle that's called Murray's Law. So there's a very specific mathematical ratio between the diameters of those vessels. And we had an opportunity to work on an idea a few years ago. We were asked to join a tender for a water treatment facility. This was one of their existing plants, and when I saw that, I thought, wow, that doesn't look very efficient. That's very rectilinear. There's a lot of space between the elements. So with one of my colleagues, we developed a tool based on that principle in nature, Murray's Law. So this shows a hypothetical layout. The white circles are bits of equipment, and then there's a pipe layout that connects them. And what this design tool does is it optimizes the relative positioning and the branching angle of those pipes. And if you look at the figure in the bottom left-hand corner, you can see that the length of pipework came down from 100 to just below 64. And then we went a step further and we ran this optimization with a real layout. So these are all the right elements in the right sequence. And this time, we combined the figure for length and angle into a figure for total equivalent length. That's actually a very good measure of the amount of friction in the system. And you can see that we came down from 100 to well below 40%. And that, I think, shows just how much we could learn from nature to make our systems and infrastructure and industries and cities far more efficient in the way we use energy and conduct resources. And to draw together some conclusions now, I think biomimicry at its best is far more than just using kind of ideas from nature to develop innovations with performance benefits, those are valid, but I think we can go much further. And rather than just creating standalone biomimetic buildings, we actually need to create buildings that are fully integrated into their environment. And I sincerely believe that we can rise to a kind of new role as human beings, a role as a keystone species that actually enhances life for other species around us. And if you doubt that that's possible, if you doubt that we can get to this point of being net positive and acting as a responsible species, well, look at the difference that a single pair of beavers can make to a fire-ravaged landscape. We ought to be able to do this. We're an ingenious species. And if you doubt that we're capable of doing this at large scale, well, look what was achieved in the lowest plateau in China. 15,000 square kilometers of barren land restored to biodiversity. And if you still feel daunted by the scale of this challenge, then consider this. I think we really could be the first generation to witness the great return. The return of flora and fauna to our forests, the return of salmon runs to our rivers, the return of wildlife to the deserts, and a rewilding of the human spirit. All of that is within our reach if we take on a new role as humans, as co-enablers of the flourishing of all life for all time. Thank you.